Welcome to ece351 Compilers. I'm Professor Ari Gerfinkel. This is our first lecture. If you're seeing it, then you found a way to watch it. The way this will work is I'm going to be live streaming during the lecture hours, which is Monday and Friday at 10 a.m. The lectures will all be recorded. They'll appear on Twitch, where the live stream is going. I will stay there, I think, for about 10 days, and then Twitch deletes them. I'm going to also record them and archive them on YouTube, where they'll remain, well, at least for the duration of the course. If you're watching me live, do go on CampusWire, join the chat. This is a way for you to ask questions and for us to communicate. If you're watching it offline, which is perfectly fine, if you do want to see the questions, again, go to the chat room. There's going to be a chat room for every lecture, and you can ask questions during the lecture or after. If you ask questions after, do say what time you're asking about, so I can look it up and just see what, say, slide or what minute the question is about. And then I guess part of the setup is that there's probably a delay between me and you, usually about a minute, maybe less. So don't be surprised that if you ask a question, I sort of reply to it a little bit later. In different places, I'll stop and try and sync with you and see. Actually, so I'm just going to pause right now. And whenever you hear this, just type something on the chat that I know what the delay is. Is somebody typing? Yeah, okay. So the delay is actually pretty small. All right, so let's start. So this is ece351. This is compilers. We have a lot of ground to cover today. There will always be typos. So of course, this was constructed on September 9th, but this is September 10th. So not writing. Oof, this is annoying. I didn't expect the annotation to disappear. So I'm going to start with a territorial acknowledgement. You probably all know that we live and work on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. University of Waterloo is situated on Haldimand Tract, the land promised to the Six Nations that includes 6 miles on each side of the Grand River. If you're wondering, this is where Waterloo is, and we're right in the middle of that tract. If you first time you're hearing this acknowledgement, look it up and learn why we do it. Okay, so this course is about compilers. So the first question I'm going to answer is, what is a compiler? So a compiler is simply a program that transforms source code to machine code. It takes code as input, and from that perspective, code is just a bunch of characters, just a text document, then an output something that actually runs on a machine. So what it means that it needs to be able to do the following sort of 3 main things. It needs to be able to take text, understand text, break it down into different tokens, break the tokens into a structure. This whole step is called parsing. What you get at the end of a parsing is you get structured text. So think of an HTML document or an XML document. You add more structure to it. That structure is usually represented as a data structure, as a tree. And then you take that tree and, the compiler takes a tree and optimizes a tree, trying to translate it from whatever, say, the programmer written to something that is equivalent, but either runs faster or takes less memory or in some way is better than the programmer had. And then after that, it transforms this into a structured output, the code generation. And often this transformation happens multiple times. So we'll see that in a sort of tradition, in a modern compiler, you go not just parse tree output, but rather parse tree output into intermediate representation, optimize intermediate representation, go to maybe several stages of intermediate representation, and then eventually you get into machine code. That's a code generation. So this is what the compiler is. What we're gonna spend today is talk about the course, the structure of the course, everything that's expected, and then sort of expand on this part of what a compiler is and look at the different parts. It's just going to be an overview of that. Okay, I was trying to do something new with the way I present, so apologize for all this confusion with markings and disappearing markings. So first thing that I want to do is I want to introduce you to our TAs. This is a big course. There's 2 sections. I think there's 200 plus students. So we have 4 TAs in total. All TAs happen to be part of members of my research group. So you'll see that all of the research topics are kind of similar. This is not by chance. They're all my students. This is also my research area. So first, there's Hari Govind. He's a 3rd-year PhD in automated program verification, which is what I work on. It says that his hobby is soccer, running, rock climbing, and biking. He's been taking this course multiple times. This is his 3rd time, so he's sort of the most versed, not just in the course material, but also in the particular structure of this course. We'll talk about labs, what you have to do. So he would be the most experienced person with all of these questions. Now, second TA is Nam Le. He is a 2nd-year PhD student. He's working on everything that has is on the intersection of machine learning and automated reasoning. So either using machine learning in order to have better algorithms for reasoning, or using symbolic reasoning to understand better machine learning systems. So for example, finding adversarial examples. He's also TA'd this course before. This is his 2nd time. So he's quite knowledgeable about sort of the logistics of the course. All the TAs are knowledgeable about compilers themselves, but not all of them have done this course before. The 3rd TA is Yusun Su. He's also a 2nd-year PhD student. He's working in program analysis. He's working in an area that's closest to the topic of this course. Once we get to optimization part, that's basically his research area. He says he likes gaming, photography, and travel, and this is his 1st time TAing this course. He's also a local Visual Studio Code expert. So if you decide to use Visual Studio Code for the labs, he's the person to ask about the setup. Then finally, we have Siddharth Priya. He's just graduated with a master's degree in my group doing program analysis. He's particularly interested in new languages like Rust, and he's starting a PhD this term. And this is his 1st time TAing this course. So this is our TAs. Now let's see. So what we gonna do next is we're gonna go about all of the different parts of the course that you have available to you. There's a lot of material. It's a bit overwhelming at first, but once you sort it out, you'll see that everything is laid out. You don't need to read all of it at once. Everything is carefully designed so that it's easier for you to follow what's needed. So there's 3 big PDFs that you sort of have available to you right now. We'll see where they are. One is the course outline. This is what we're going to go over today. I'll tell you what is the expectation for you for the course, when we have what kind of assessments, what are the assignments, and so on. It's a big, long document. We'll do that today. Now, in addition, there's course notes. So this guy here. This is essentially a book on compilers. So it's a collection of material from different books that Professor Derek Rayside put together. This is what essentially you have to read before every lecture on Monday. There's going to be a section that we cover. This is the main reference. It's long. It's fun to read. It tries to be sort of easy for you to understand. Yeah, so that's notes. Now then, there's going to be this big document, the lab manual. That's going to be something you're going to spend a lot of time with. The course is structured as any compiler's course around a term-long project. This particular one is broken into 12 labs. We skip 2, so it's 10 labs that you have to do. Each lab involves some amount of implementation. They're designed so that you spend about an hour and a half per lab. They're due almost every week, and they take the form of assignments. And so the manual will tell you exactly what you expected to do for each lab, how to complete it, and gives you hints on what to do. And again, we'll talk about how this is going to go. And then I may release study questions before important tests. Slides is the ones that you see now. It says sometimes, but really, because we are online, slides will be every lecture. I'll post them just like I did right now. So they'll appear probably somewhat before lecture, fairly shortly before the lecture, just because I'm always updating them and changing them right before. And then there is no book, but again, I'll recommend some books if you find that you learn better with a book. Okay. Next. Right. Okay. So everything that is going to be distributed will be distributed through Git. There's lots of repositories that you have to manage through the course. There's one repository with all of the PDFs materials. Instead of the website, I'll just post things in a Git repository in here. I'll show you how to access it in a second. But most importantly here is make sure you have an account at gituwaterloo.ca. I think I checked yesterday, and except for maybe 5 people, everybody had one. I emailed the 5 people that don't. So if you got an email from me saying get your Waterloo account, please do it as soon as possible. Okay, and so I want to acknowledge that a lot of this course material is originally developed by Professor Derek Rayside and his staff for ece351. I really like the direction that he took with the course, the way he teaches compilers as a mix of compilers and programming. And so I'm following his notes for that reason. And then I'm supplementing with some materials from Professor Vijay Ganesh. I take full responsibility for all typos and errors. So if you see typo, it's probably me modifying some of those things. Okay. So next, let's go and see where do you get things about the course. If you have questions, speak up. But if not, let's go and explore. So first of all, we're using CampusWire. So you should see my CampusWire chart right now. If you've never used CampusWire, but you've used Piazza, CampusWire is like Piazza, but better. I've been using it for a few years now. It's glitchy sometimes, but if you see a glitch, just tell me, and I can report it to CampusWire developers, usually quite responsive. I remember some years a search function didn't quite work and was quite annoying because you couldn't find older posts easily, and they were quite quick to fix it. I like it because it gives me much more flexibility than Piazza. Like we can have our chats. I have a phone app, so if you ask a question, no matter where I am, I usually see it quite quickly and can respond quite quickly. It has more functionality, especially now with COVID, that appeared than I use. If you see some functionality that you think would be useful in a course, but I'm not using, for example, I haven't filled the calendar and things like that, then do let me know and we can try and use it. They do have a way to stream lectures. I haven't tried this. I have my own setup, like the stream and what I'm doing. And so it's quite difficult for me to switch to different systems. So that I will not do. But other features, if you think they're useful, tell me. So here in a class feed in CampusWire, there's going to be all kind of announcements posted. Sure, you can figure out how to use it. There's a pinned message with important links that tells you about all the other things in the course. I'll post a message before every lecture with where to go for lecture, how to go to the YouTube archive, and most importantly, the link to the chat room. If you live and you're in chat, you know, but if you happen to watch this at some other point, or maybe you watching it on Twitch and you don't even know about CampusWire, get on here. Now, in addition to this, we have a whole bunch of Git repositories. We have a group on Waterloo's GitLab system. If you don't know about GitLab, but heard about GitHub, And sort of GitLab is a free version of GitHub that you can install on your own. And Waterloo maintains a server. Each one of you gets a repository in there. So you see that I get to see all of your repositories. You, of course, see far fewer in here. You just see the ones that belong to you. The repositories that you have, so I'm going to go to mine, will be a way for us to collect all assignments. So you'll see in the lab manual, the way you submit anything is you just push files into this repository. We then go into it. Since everything is timestamped, we know when you pushed. We take the code as it is by the deadline from the master branch. We use that code to mark. Now, you can use this repository any way you want. You can create additional branches. You can put additional files in there. You should, save your work there as often as possible. The important thing is that we're going to mark the master branch at deadline. And so please make sure that the master branch at deadline works and compiles. What people sometimes do is they run ahead, and when they finished one lab, they start on another. They put their code still on the master branch, and then by the time of the deadline, they have all of the old lab working, and maybe half of a new lab done and doesn't even compile. And then if we take that code and try to mark it, we just see compilation errors, and then we have to penalize you for that. So the way to do this properly is you should probably run a separate branch called dev or something like this, where you commit things which are not ready, and you merge that branch into master whenever it's ready to be graded. Now, in addition to your personal repository, there is a skeleton repository called skeleton. This one will contain the assignments for the labs. The master branch of it will always be for the lab that is due. There are other branches for labs which may have passed or future labs. So right now, lab 0 is released. Lab 0 is something that you have to do. Look into the lab manual and you'll see what it requires. It's really just a setup lab. There's not much you have to do. Just set everything up and make a commit into a repository so that we know that you got a Git account, you know how to use it, you have a good setup. The master will always be, or the skeleton will always be the latest lab. And then as the course progresses, I will start releasing future labs so that people who want to run ahead can go and do a lab that is not yet due. Okay. And then finally, maybe the most important repository, at least for today, is the one called PDFs. And this one contains all of the PDFs, all of the information about the course. So there's going to be an outline, which is what we're going to look at today, notes, which is the lecture notes, manual, which is the lab manual. So what you should do after today's lecture is look at the lecture notes and look at the first chapter in there, which corresponds to what we're covering today. Look at the manual and look at lab 0 and see what it needs, what you have to do. And this is lectures slides for today. They're already in here. I'll keep updating this. I will try not to update any old files, but the lab manual and the notes may need to be updated. So if they are updated, I'll just commit them in here, and you'll see, when they changed, you'll see that there's a new change. I'll announce any change that I have to do. But I promise that all the changes will be small. So if you, for example, want to download those PDFs, put them on your iPad and read them and take notes, you won't need to update whenever I do an update. It'll probably be fixing small typos and things like that. Okay, so let me go back to my room, see if there's any questions. Okay, I don't see any questions so far. I'm going to go over the course outline. Switch to my tablet. And go into outline. Okay, let's see if we do it without the presentation mode. All right. This seems to be working. Seem to have an older version. Oh, this is not the right outline. This is an older version. Here's a good. So here's a better version of the outline. So let's see. So it tells you what the course objectives are about. So we're going to teach you about compilers, and we're also going to teach you practical skills of how to build a compiler. I'll talk about this in a bit, but let's get to the sort of the more practical matters. So one thing that you find in outline is the coordinates of everybody. So we are mostly online. The way to get in touch with me, the easiest way is CampusWire. There is an email if you need email, but I do get a lot of emails and sometimes they get lost. If you don't hear from me fairly quickly, email again. But even better, go on CampusWire. There's emails of all of our TAs. There's a lecture time right here. We're going to talk about tutorials in a second. We're going to talk about labs in a second. There's going to be a midterm and a final exam. I don't use Learn much, but I will make some first announcements in there because I know then they get to people who haven't signed up yet to other systems. This is how you sign up on CampusWire. If you haven't done that before, please do. Here's a link to the PDFs. Here's the link for the labs. All labs are due at exactly the same time. So every week that a lab is due, which is almost every week of the course, they're due on Thursday at 10 p.m. All time Waterloo time. I don't know whether you're all here or elsewhere, but whenever I mention time, if I don't mention the time zone, it's a Waterloo time zone. Now, let's see, tutorial and labs. So we have tutorials. Not that many, actually. There's just a few tutorials that are planned in the course. There is an option for in-person tutorials, but I'm not yet sure how this is going to work. This is a very large class. We can have a tutorial of everybody in one room. I think they've scheduled us by dividing you into many, many groups, into many different rooms. There's also people online, and so the tutorials have to be online. I know that there are rooms which have video equipment, so if the tutorial is in that room, then there is a video for people who couldn't make it, but apparently the equipment is not working all that great. So we're going to see how things go. At least the first tutorial is actually just a tutorial on how to get everything set up. That one is already out. It's already on our YouTube channel. It's not going to be in person. It's actually nicer when it's not in person because you can stop and follow and see what happens. And for future tutorials, we'll wait and see how things will develop with all of the COVID protocols, whether it's easy to do them in person or not. So there's no in-person tutorials until further announcements, and I'll show you on the schedule where the tutorials are. And so the first one will definitely be not in person. So the 01 has happened. The first one will not be in person, and then we'll see again. Now, the way this class usually works, there is a lot of interactions with TAs, and that usually happens during clubs. So in the normal schedule of this class, the labs are in person, and people go to lab. They usually use their own machines to do the work. They usually do the lab during that lab period, so about an hour and a half. And the TA is spending their time in the lab, and they answer the questions as they happen. We can't have in-person labs this term. So what we're going to do is we're going to try and replicate this virtually. I'm going to have a TA scheduled on a Zoom call in that period, Tuesday, Wednesday, Thursday, between this time. And you'll have a Zoom link. You can log in on a Zoom link. A TA will be there. They'll answer your questions. And then we'll have to figure out how to manage all of this. So because it's virtual, we can have multiple TAs join when needed. Unfortunately, you're not divided into these three groups, Tuesday, Wednesday, Thursday. Usually the class is divided into these three groups. But we'll see. So for now, we'll just say that there's a TA available during that time. You can come in, ask questions, and then we'll see how that goes. If you have too many questions that we can handle, maybe we'll have to have some more structured policy. Okay. Now the schedule. So lectures, of course, are live streamed as you see them now. Unfortunately, this is a very big link, but in the PDF, if you click on it, or if you go on any electronic information I release, you can click on the link. That will take you to a playlist on YouTube. It's an unlisted playlist, and I'm just going to put things in there. Right now, there's a tutorial of how to get stuff set up into the lab. This is our weekly schedule. Everything is in here. We're going to have lectures on Monday here and Friday here. As I hinted, the course is broken into sort of two parts. There is a theory of how do you build a compiler, and there's a practice. So theory will be Monday, practice will be Friday. So each Monday, we'll use the lecture notes of the book, and we'll work through something that is more theoretical in nature. And each Friday, we're going to get into the appropriate lab, and we're going to talk about practical and theoretical aspects of successfully completing that particular lab. Today, we are on Friday, and we're not doing a lab. It's an exception because we start on a Friday, not on a Monday. But then after that, you'll see it's going to be kind of the same, Monday, Friday. Everything that's marked with a TA is what's usually a tutorial. We'll see how to run them. As you see that we don't have a tutorial right now. So the first tutorial is on setup, so it's already online. The first tutorial on the course material will be here, which is a week from now. It's most likely going to be online. We'll figure out the format, how to do it. I'm not yet completely sure. I mean, it'll definitely be eventually on YouTube, but I'm not sure whether we're going to do it on Zoom or live streaming, depending on what our TAs can do. And then later we'll see, maybe we'll manage to do in-person tutorials in here. We'll see. Things like midterms reviews and midterm recap are nice to do in person. And maybe by that point, things will be clear and we can do them. Now, in the middle of a week, you see that every week there is a lab due, almost every week. It tells you which lab is due when. Lab 4 is a little bit longer, so you have a little bit extra time for it. Lab 0 is due next Thursday, so don't miss that. That's the first one to do. I'm going to release new labs after the deadline for the current one, so that you don't get confused by that. We have a reading quick. This is probably you all know about. We also have a midterm week, which is maybe special. So there is no, because everything is mostly online, there is no just one midterm week for everybody. So I'm going to take this particular week 7. I'm going to turn it into our midterm week. What that means is that the midterm is out during that time, and there's no lectures. Okay. So if you have questions about the schedule, let me know. What's new this term? One important thing is that we're switching to a new version of JDK. So all of the labs, we're moving them to JDK 11. Unfortunately, it's not completely trivial. So if you run into any kind of strange issues, something doesn't quite look like in a lab manual, or something doesn't quite work like the lab manual tells you, it's possible that this is just because we didn't port things properly. So do speak up. And also, you'll notice that all the lab manual are developed for Eclipse. But this year, we're also starting to use Visual Studio Code, since Eclipse is becoming less and less popular and Visual Studio Code becomes more and more. As I said, we have TA Yusen, who is an expert in Visual Studio. He got everything set up and running. But again, that's the first time we're doing it in the course. So again, if you run into issues, or if you want to use Visual Studio Code, expect maybe some issues, but also hopefully we can support you. Marking scheme. That's probably most interesting for you. So first of all, the marks are divided between the labs, so assignments that you do, programming assignments, and sort of pen and paper tests. Of course, everything is online. The division of marks is slightly towards the labs. There's lab 0. The 1% here is just to ensure that you actually do the lab and don't skip it. There's really no much work you have to do. The labs grades are split into 2. There's a grade at deadline and grade at the end of term. And the idea here is to give you an opportunity to improve if for some reason you are not able to get to the lab at a given time. The labs are cumulative. So whenever to do the next lab, you do have to finish the previous lab and you do have to get it working. But, things happen, and maybe by the deadline, it works somewhat, but not perfect. Or maybe once you see your marking report, you realize what you've done wrong and you want to redo it. So what we're going to do is for every lab, we're going to mark it at deadline. You're going to get some mark. And then at the end of a course, we're going to take a repository that has all of the labs done, and we're going to run the marking scripts again. And that's going to give you a new grade. And then we're going to take for each lab a grade that it received during deadline, and then the grade that the marking script gives it at the end of the course. And we're going to take 20% of the first and 30% of the other, and that's going to be the grade for the lab. So basically, if you do the lab at deadline and you've done it perfectly, then you're going to get full marks at deadline, and you don't need to do anything. You're just going to get the same full marks at the end of a term, and you have full marks for the lab. But if on the other hand, you somehow weren't able to do things at deadline, then you get not full marks, but by the end of a term, you were able to fix it, and now you do get full marks. So you're going to get the appropriate weighted sum of this. We assume that nothing is going to break at the end of a term, so you cannot get lower grades. So it's not possible that your grade at the end of a term will be less than the grade at the deadline. So this is the labs. Now the written things. Okay. So we have quizzes, and there was a question about deadline for quizzes and things like that. And again, quizzes are kind of like lab 0. The first quiz will be released next week. You'll see what it is. It's really a way for me to kind of quiz you, ask you about how the course is doing, give you a few technical questions, but very few and not very complicated ones. And the grading is really just, again, so that you complete that part. So don't worry about quizzes. They're not there to make your life harder or give you more things to do. I'm expecting that you can do them virtually without any preparation, and everybody is going to completely succeed in them. And the grades are there just to make sure that you actually do them. And then we have a midterm and a final exam. These are more serious. This is kind of your traditional midterm and traditional final exam. There's going to be lots of questions. You have to answer them. In terms of logistics, we're going to do it over Learn. Learn has a quiz interface that seems to work fairly well. You've probably used it. I'll expect you to either answer online or answer on an iPad or paper and take a picture and then upload those pictures onto Learn. I've done it for quite a few times now with all the online teaching during COVID. Seems to work quite well. The logistics of actual midterm and exam will be that you'll have a whole week to do them. Doesn't mean that you can do a little bit every day. It just means that I give you a week and you can pick when during this week you want to do. The assessments will be timed. So once you start, the clock goes on and you have to finish within a certain time, different time for midterm and an exam. Extra time will be given so that you don't have to worry about uploading all the pictures and all of those things. So that's on top of the normal exam time. And that's pretty much it. So you get to pick when exactly you want to do it during that week. It's going to be usually 2 or 3 hours, depending on what it is. And yeah, you just do them on Learn. So let's see. Right, there's a bunch of minimums built in, so you have to pass the labs and you have to pass the test in order to pass the course. Again, most of these rules are here just to ensure that you don't decide, oh, I'm just going to skip one or the other. Like I'm going to do my labs and I'm going to get 51% and then I'm done and I'm not doing any midterms and final exams. If you get past all the labs and you do a final and a midterm, you'll pass the course. So don't stress too much about that. We talked about online. Again, there's a link to the reference material. Let's see. So then textbooks. We don't have any textbooks for the course. Everything that you need is really in all of these materials that I'm giving you and the lectures. But a lot of this material is really sort of core compiler material. You'll find a lot of references online. It's usually more accessible than a book. If you do want to read a book, this is a book that I use myself as my reference. The other books are also good, but if you were to pick one, that's the one I would go for. We have an interesting collaboration policy. I'm not going to go into it right now. You can read it on your own. The important thing is don't cheat. Cheating is bad. The consequences of cheating are terrible. Just don't. So if you're struggling in a course, if you have problems, come ask for help. One way you can ask for help is this collaboration policy, where you can find a partner who understands the course material a lot better, who may be able to help you in a lab. This, of course, will cap your mark, so you will no longer be able to get 100% in the lab. But the cap is not that bad. The cap is 85%, and you get help. We read about this policy. The point is, don't cheat. If you feel overwhelmed and it's really hard and you just don't get it, ask for help. There's ways to do it without just copying somebody else's solution. We're not in person, so the classroom conduct policy doesn't really apply, but really just pay attention and you'll get a lot more out of the course if you pay attention to the lectures rather than doing something else in addition to that. Okay, so we had acknowledgement, and you all know about the academic integrity and other policies. All right, so let's see if we have questions on the outline. Okay, so let me ask to tell me when we are in sync. So is the delay really that bad, or nobody is willing to say something? Oh, great! We are in sync. I do want you to, to not be afraid to type and do not be afraid to ask questions. It's gonna be a lot more fun, both for me and you, if I can see you asking questions and you actually interact with me and questions do get answered. And I want to remind this, I said this in chat, but do put a picture to your profile on CampusWire. This is one of the things I miss the most. I don't get to see you. I don't get to see how much you actually follow, don't follow what I'm presenting. At least if I see a picture of you, sort of have some connections to who I'm talking to. Okay, so we finally got into sort of some of the more core material. So we're going to talk about, just in general, compiler, stages of compilation. Let's see how far we can get today. All right. So this course is, of course, about compiler constructions. So what that means is that we're going to learn basic concepts in these topics. First is formal language theory. So this is what are regular and context-free languages. and their properties. Then we're going to look at the stages of a modern compiler. There's lexical analysis, we'll talk about shortly, context-free grammars, parsing, which is a process of converting stream of characters into a structured representation, and then what a compiler does given that structure. So the parser checks that the code is well-formed, but only well-formed according to the parsing rules. You then need to go deeper and check that it conforms to various semantics rules. First of them is type checking. So for example, that you're using numbers where you're supposed to be using numbers. Then there is static analysis that goes deeper than types to check properties of code. Then there's code optimization, which is restructuring code in a way that it's better in some way, usually speed, but not always speed. Then there's code generation, which is targeting the code to a particular architecture. And then for, depending on the language, it could be also memory management, like garbage collection and runtime support for those kind of things. So what's a programming language? Well, it's a powerful mathematical construct that lets you express an algorithm that you want computer to do. Each language has two aspects. One is syntax, which tells you what is legal to write in this language, what at least makes sense syntactically as a collection of symbols. And the second is semantics. And semantics determines what the language really means. Usually we think of semantics as something called operational semantics, which is an explanation of how a program makes certain machine operate. The syntax tells us how do we write things that make sense. Semantics tells us how it operates a machine. So a program could be, say, syntactically correct, but semantically it may crush the machine, and we'll say, well, that program is not correct, not good. Of course, semantics assumes some model of computation. We usually imagine something like a normal computer and von Neumann machine, but you can imagine other computations as well. Now, as I said, we're going to use operational semantics in compilers. That's a usual way to interpret languages. But actually, it's not the only one. There's lots of other ways. There's denotational, which really means interpreting a language using mathematics. Instead of a computational machine, you interpret every program as a mathematical function. And then there's axiomatic, where you interpret every function, every program by the kind of properties you can prove about it, by the kind of specification that it has. But in this class, operational semantics, that's the one we're after. We just want to take text and make it work according to the operational semantics. Now, there's lots of types of programming languages. Usually we divide them into declarative and imperative. Declarative is a language where you specify what you want rather than how. And imperative is where you specify in addition to what, the how. If you want to think of a declarative language, the one that you're probably familiar with is SQL. This is a language of queries to extract information from databases. What you write in SQL is essentially a program that tells you how to fetch data from the database, but it's stated declaratively. And the compilation process is quite complex because it has to go from this declarative statement to the how to do it, how to generate the plan of execution, and then eventually compile it to a program that runs. An imperative language, the compiler job is a little bit simpler because you already specified how you want to do something, not just what you want to do. And a compiler really just has to convert this from maybe a higher level description to a lower level that a machine can do, and maybe optimize a few things in the process. And then other features like object orientation and other things that we add to languages, they usually can be added on top of. You can have a declarative object-oriented language or an imperative object-oriented language. They can be combined with this feature. Now, a good programming language design is, of course, not easy because we have to satisfy lots and lots of different constraints, right? We have to enable programmers to produce efficient code And this by itself is really hard because programmers are people, different people understand things differently. For example, some people really like declarative languages and it really speaks to them. Others really like imperative languages. There's a big debate always about which one is more productive. But I think it's very much depends also on the person working on it. And then we have to satisfy lots of other things. We have to be secure, correct, discourage bad practices, make it easy to write good programs, make it hard to write bad or hard to maintain programs. Now, once we have a language, so in this course, we're not looking at programming languages, we're looking at compilers. But once we have a language that somebody designed, we have a choice of how to implement it, how to get it to work. We have two choices, well, three now. We can interpret a language, we can compile a language, or we can mix. Okay. The interpreter is really easy. It means that we're not really compiling the language into machine code. Rather, we have another program called an interpreter. It reads every instruction in the language, and it does what this instruction is supposed to do. You probably know a whole bunch of interpreted languages. One that comes to mind immediately is Python. Another one is a Java that's interpreted by Java Virtual Machine. Another one is JavaScript. To some extent, SQL is interpreted. The problem with the benefit of interpreted languages is that they're easier to work with from the programmer's perspective. Debugging is a lot easier because the program runs not on a bare metal. It runs on some virtual machine, on some interpreter. So whenever it fails to run, whenever it crashes, the interpreter can give a lot of information. The interpreter can run in a special debug mode, keep track of what the program is doing, and really help understand what's happening, why, for example, it is failing. The cost, of course, is that it is slower because everything is interpreted. Everything goes through an extra interpreter as opposed to running directly on the underlying hardware. This is where compilers come in. So languages which are compiled, it means that they're converted first into machine instructions, and then they run as native machine instructions on the machine. Languages like this are languages like C and C++ would be languages which are compiled. Usually, the reason for compiling is performance. If performance were not a reason, we'd always have interpreted languages. They're just so much easier to work with. Now, the way to get performance into languages which are interpreted is something called JIT, or just-in-time compilation. And in this case, the interpreter ends up being also a compiler. So what happens in just-in-time compilation is an interpreter, whenever it runs a program, usually it looks at the level of functions. And if it sees that a certain function is being called multiple times, then it will compile this function into machine code. And then it will remember that machine code. And every time this function is called again, instead of going and interpreting every instruction in the function, it will just call that machine code. It will recall that machine code and let it run. And when the function exits, then it looks at what next things to do. This is what, for example, is done in Java, and I think to a large extent in JavaScript as well, where we're making the interpreter to be also a compiler. Right, so we talked about what a compiler is again. So we translate the program from high level to low level language. Now, during this process, the compiler must check that the program is correct to some extent. So for example, that it's syntactically correct, that it's typed correct. Not all the way that, for example, it doesn't crash, but to the extent that is possible. The reason why compiler doesn't check it all the way is because the problem of actually verifying program completely is undecidable. Many programs where we just verify program not completely, but just deep enough, end up being very expensive. So the best algorithms that we have are exponential. And so the compiler must balance, must keep this balance between being fast itself, so that you don't have to wait days for a compilation. At the same time, try to do as much analysis as possible to catch as many potential problems during compile time. Then the compiler will optimize the code. If it did some analysis to understand what the code is doing, it may be able to restructure it to achieve the same effect but faster. Links all the libraries, generates a binary code, and then outputs an executable. Now, the executable is supposed to be functionally equivalent to the input program relative to its operational semantics. Basically, what that means is that when you look at the program and you look at the text of a program as a programmer, and you kind of understand what it's supposed to do according to the specification of a language, then when you run the program that is compiled by the compiler, it should behave exactly the same as you expect from the language specification. Now, right, so what kind of implementations we have of it? So most compilation is done using batch systems. So if you've used the compiler, maybe the famous one is GCC, and the new one that's coming around is LLVM and Clang, which is what's used by the Xcode on Mac. They're languages which are primarily interpreted. So Java, which is the language we use in this class, Java bytecode is interpreted. And then, of course, all of the dynamic languages like JavaScript, TypeScript, and Python are interpreted. Some systems do provide both. I think Python, you can actually compile to a binary. Systems like OCaml provide ability to compile them to both interpret and compile to a binary. And languages like Lisp do that as well. Now, how did we end up with this high-level language? Well, we didn't start with that. Everything, of course, starts with engineers. They build machines, and they want them to do things. And then eventually they discover that actually programming these machines can also be quite important and quite expensive. So in 1954, IBM developed what is known as a 704, which is, as you see here in the picture. And the problem was that because all the programming was done in assembly, the software costs exceeded the hardware costs. And so that's a big problem because building this hardware was revolutionary. And then the software is kind of just simple math to get stuff to work, but somehow it ended up being more expensive. And so this changed when John Backus entered into the picture. And he proposed something called Fortran, which stands for Formula Translation. And the idea was that perhaps instead of writing everything in assembly, we can write things in a higher level language. And then the translation to assembly, the translation to the details of a particular machine, can be done automatically. Now, at this point, people thought that this will never be possible. That a smart human figuring out how to do things in assembly just cannot be replaced by a machine. That just the code will be too inefficient and impossible. And others have tried that before, but up to this point, there wasn't any established compiler. And so Fortran was developed between 54 and 57. And by 58, apparently 50% of all software, more than 50%, was already written in Fortran. And the effect that it had is that the development time for new software was sliced in half. And there was cost of performance, of course, and doesn't come for free, but the performance was reduced only by 20%. And so it's quite manageable if you can produce more code. And this has been sort of repeating again and again. If you look at new modern languages, there's this big push to get into new languages, which makes it easier for the programmer to manage. A language like Java, for example, when it appeared, its big downside was, well, it's going to be a performance cost compared to something like C++. But its big advantage was that the programming model is simpler, development tools easier, and that it's going to be much more productive. So people can write the same piece of code faster and know that it's going to be of higher quality. And so performance is not an end-all for everything. And even now, if you look at embedded systems, there's quite a big push to use languages like Python, which from performance characteristics is just terrible. Like, why would you put something so slow in an embedded system? But it increases productivity and makes it easier to do what you want, and the hardware can just be improved so that the difference in speed is not as important. Now, Fortran was the first compiler. This project had a huge impact on all of computer science. It's just amazing how much theoretical work that came from the team of Fortran and just from the work. And it's still everything that we do in compilers is really influenced by that. The outline of modern compilers still follow the same outlines as Fortran. The only maybe big change is syntax. Fortran had a particular style of syntax which wasn't really really good. Nowadays, a syntax that came later with C dominates much more. But everything except the syntax we really can trace back to this Fortran work. All right, so then how does it work? What are the phases? So we have lexical analysis, parsing, semantic analysis, optimization, and code generation. The first three phases, which are these three, is really can be understood the way human understand text. You look at say a story in a newspaper. First, you do some simple analysis to figure out where each word begins and ends. And then you're going to go and take those words and put them together into sentences and understand where the object, where the verb is, and what the sentence means. And then you're going to read the sentence after that and try and see whether it actually makes sense semantically, whether it's just gibberish collection of words or whether it has some kind of meaning. And it's the same that the compiler is doing. And sort of historically, the way this came, the analogy was exactly with trying to see how humans understand it and trying to see how we can explain how a compiler should do. So this is how this general flow looks like. We have an input program in here. We have an output program in here. We have lexical analysis. So what it gets in here is just text. So just a stream of characters. What you get outside after lexical analysis is a string of tokens. So again, think of a newspaper article. What you get as an input is just symbols. And after lexical analysis, you will have individual words separated. And things like white spaces, new lines, all of those things stripped away and removed. You then have a parser. And a parser output something called an abstract syntax tree. Now we'll talk about what the abstract and syntax is. So the important thing here is really that it outputs a tree. So it breaks, it puts these tokens into some kind of order and says that they have different meanings. And then now this AST goes into this next box, which is semantic analysis, which now looks at the structured input and tries to figure out whether it makes semantic sense. So in programs, it would be whether everything is typed correct, whether you're using, say, integers where you're supposed to use numbers, strings where you're supposed to use strings, whether when you call a function, the function is actually there, and things like that. And then the output of this is usually something called an intermediate representation, which is a representation of the program, which is already structured, but in a language which is simpler than the input language. So usually this is the core of the language. It has enough to express every operation that you need to do, but maybe without the syntactic sugar that you usually have. And maybe with additional annotations to make it easier to work with, but maybe more tedious to write. And then this intermediate representation goes into code optimization box. That optimization box now looks at this and sees, can I rearrange things to make things better? Maybe I can inline functions. Maybe I can remove some computation because it is not used. And eventually get code that behaves functionally the same as an input, but is better. And again, usually better means speed, but not always. Sometimes we want to optimize for size instead. The output of code optimization is what is known as a 3-address format. This three-address format simply means that the program is further broken down so that every operation has only one side effect. So for example, something like this will say a 3 address because there's 3 addresses that are used. A variable y and z are read, and a variable x is written. Whereas something like this is not 3 address because now we have 4 different things working. As you could see that the code optimizer will maybe take expressions which are complicated and large, and it will decide in which order to evaluate them in such a way that every evaluation step is now simple. It reads at most 2 pieces of memory and it writes at most 1 piece of memory. And then the code generation takes this. The 3-address code is very close usually to what a machine can do, and it generates a program. Now we'll spend the whole course talking about this component, so you'll learn a lot more details about them. So let's see, we still have a bit of time, so let's do a little bit of lexical and parsing, and then we'll continue in the next lecture. As I said, the goal of lexical analysis is to recognize tokens, to take a stream of something very low level, like characters, and turn it into a stream of more meaningful things. So here, for example, we have this purple thing, which is just a sequence of characters. And the lexical analysis would go and try and figure out, for example, how to break it into words. That we have this word 1, word 2, word 3, and word 4. That's the goal of a lexical analysis. So, of course, in a programming language, we can go further, and it's not just going to be arbitrary words, but some words we can assign meaning to. So we have things like keywords, operators, constants, white space. And so as a lexical analysis goes, for example, it will divide this and say, look, this is an if statement, and this is a variable, and this is an equal sign, and this is a variable, and this is a special then keyword, and this is a variable, and this is an assignment, and this is a number, and this is a semicolon. So this annotation, breaking the stream into this individual things, that's what the lexical analysis does. Each individual thing here, instead of using a word, we call it a token. And each token has a type, its kind. So whether it's a keyword or a variable, and then it has the content that it represents, the textual strings that correspond to it. And when parsing starts, it works not with a string of characters, it works with a string of tokens, and then it tries to put the tokens together. So for example, when parsing this sentence, after lexical analysis, you would look and say, ooh, I have something where the start of this something is an if keyword, as opposed to if character. And the reason for doing so is really just to separate the two parts. It's easier to parse things out of bigger chunks than to parse them out of little individual words. Okay. So once we broken our program into words or tokens, the next step is parsing. And analogous to what we do in human understanding, parsing corresponds to diagramming a sentence. And perhaps you've done this in grade school, where you go and you assign to each part of a sentence different pieces. What's a verb, what's an object, what's an adjective, and where they are. So let's look at an example. So we have this thing called this line is a long sentence. It's clear for us what the tokens are, right? They're separated here on the slide. So each purple thing is an individual token. And so now we have to put them together and see whether this collection of tokens actually makes a sentence. How do we know that this is a legal sentence in English? And this is what diagramming does. It goes and attaches to each token what is its interpretation is inside an English sentence. So we know, for example, this is an article, line is a noun, is a verb, a is an article, long is an adjective, sentence is a noun. So now we at least see that inside this sequence of words, there are nouns and there are verbs. So maybe we can have a sentence, depending where noun and verbs are and how they're positioned, how many verbs we have, how many nouns we have, where we have articles and things like that. So next, we can separate this and we can say, oh, an article and a noun is a subject, and an article and an adjective and a noun is an object, and the two are connected by a verb. So now we have more of a structure of this thing. So we're building a tree that tells us what first each individual token is, and then we, because the tokens appear next to one another, relative to other tokens, we can give them more meaning. And then out of this, we get a sentence. So when we diagram a sentence, we're essentially saying a sentence is a subject, a verb, and an object, exactly in that order. That's one thing to be a sentence. You have to have a subject first, then a verb, then an object. And then we're saying, what's a subject? A subject is an article followed by a noun. That's one way to be a subject. What's an object is an article, adjective, and a noun. That's another way to be an object. And then a verb is just a special keyword is. That's what a verb is. So this is how it works in English, and this is exactly what a compiler needs to be able to do. So as a compiler designer, for example, we need to express what do we mean by all legal sentences. Do all sentences have subject, verb, and object? What are all possible subjects? What are all possible verbs? What are all possible objects? We need a concise way to state all of this. And then we need to implement a parser, which is something that takes a sequence of tokens and tries and tell us whether the sequence of tokens fits into our language by diagramming, or what we call in compilers parsing that sentence. And in order to show that this input parses, we would need to have a parse tree, which is this diagram, or an abstract syntax tree that basically tells us how the input corresponds to something in our programming language. So here's an example of an if statement that we saw before. This is how it looks like diagrammed. So we have this guy, and we'll say, well, this guy is a relation because it's a variable followed by an equal sign, which is a special token, followed by another variable. And so that's what a relation is. It's two variables separated by a comparison token. We have an assignment, which is a variable followed by an equality token, followed by something that's being assigned, in this case, a number. We have another assignment. And then we have an if then else statement, where an if then else statement is three pieces. It is a predicate, followed by a then statement, followed by an else statement. And now we can connect the two. Well, a relation is a predicate, so one kind of predicate is a relation. An assignment is one kind of statement. An assignment is also, well, it can also be an else statement. And so now we have that we can parse this string, and we can say, well, this string matches what we mean by an if then else statement. So it's something that can be broken into predicate, then an else statement, where predicate is a relation, and so on and so on. So this is the parsing. All right, and so let's stop here. End of lecture 1. And so on Monday, we're going to continue with this. Remember, our Monday lectures will be more of this kind. So we're going to look at more of a theoretical aspect. And then on Fridays, we're going to look more at the labs and the implementational aspects. Don't forget to do Lab 0, which is out right now. Most important thing is do follow the videos or the manual. Get the Java environment working for you, and let us know if you run into any problems with it. Oh yeah, one other thing I forget about questions. So this is a big class, and if you ask questions privately, it's very hard for us to manage because we have quite a few TAs, but still there's many more of you. So if you can, please ask your questions publicly. So the best way is just ask a question on CampusWire so that whenever we reply, everybody else can see, and maybe others had similar problems and they found a different solution and can help you as well. Of course, if you have private questions, then do ask them privately. But whenever you ask a question, first think, should I ask it publicly? CampusWire does allow you to ask questions anonymously. So if you're just worried and you don't want to disclose who you are, just use anonymous. There's a question about whether my annotations are saved on the slides. They are, but I usually don't post them. I find that I sometimes put too many annotations and then the slides are hard to read. And with the video lectures, the videos are there, so you can always go to the appropriate part in the video. And if there's some annotations which are helpful for you when reviewing the slides, you can see them there. If there's going to be a request to post marked up slides, or maybe marked up slides for a particular lecture, let me know. I believe the way it's set up right now is that every time I do any marks, they will be saved. Actually, it depends. So some slides are PowerPoint slides like this ones, so then they will not be saved. But for PDF slides, they will be. Yeah, so basically, let me know. I prefer not to have annotated slides because then you have to have 2 copies because annotations sometimes are too much. But if annotations are helpful, let me know and I'll figure a way to post them too. All right, so I think that's it. Yep, let me know what you think of the lecture, especially if something doesn't quite work. Yeah, please feel free to comment. Okay, thank you guys. I'll see you on Monday.